And we first encountered Bessel's equation because we were talking about solving partial differential equations by separation of variables, really powerful technique, but it might not necessarily come out of the context of just the spheric or cylindrical polar Laplacian. So in general, Bessel's equation looks like this, up to some trivial changes where I could like divide this by x, which is what we saw. We had 1 over rows in the separation of variables problem. And I could just multiply the whole equation by x or rho or whatever to put it in this. This is the standard format. Okay, and just as a note, if you're trying to map this onto the thing that we talked about before, you should realize that what we're calling x in the standard form of Bessel's equation is what, from the separation of variables treatment of the Laplacian, is k times rho, where k was the separation constant. Technically, k squared was the separation constant, because we kind of knew what we were talking about. We had 2 derivatives. When we peeled off the z part, so when we split those 3 variables, rho, phi, and z, we ended up with something that looked like this: z double prime over z equals k squared. We just decided to call it k squared plus or minus, with z being the function of z only. So if you want to just complete the mapping onto the standard form, you would have to do that. Okay. So the point is this is a differential equation, and its solutions are Bessel functions. So depending on what nu is, it could be Bessel functions of a certain type. Let's just consider nu to be an integer for now. So what we're going to do is treat them the way that physicists need to treat them, and just say like, okay, I see this equation, I know what the solutions are, and then I'll just like look up the properties of the solutions. So that's where we're at. And you went through the hard work of doing the indicial equation and all that stuff. But at this point, it's like see Bessel's equation, know that Bessel functions are the solution, and then know their properties and piece together whatever solution you want out of them. Okay, so this is what they look like. And I'll post this if you guys want, but it's just kind of a light edit of what you would find online. So this is just a plot of the first 5 Bessel functions. And I want you guys to kind of think about a drop of water falling in a still pond. The ripples would look like this. This is a Bessel function solution. But I also want to notice that the black one, they're not labeled. The black line is J0. So J0 starts at 1. And then all of the higher j's start at 0. So if you're solving an initial value problem, like, you know, another Bessel function solution is a circular membrane or drum head or something like that, hit that, and the vibrations will be Bessel functions. Only J0 starts at non-zero. So if you're piecing together a solution, just remember that. The other thing to notice that's not obvious is that sines and cosines have very regularly spaced zeros. Right? The zeros are separated by 1 wavelength. Bessel functions do not. And there's no closed form solution for the zeros of Bessel functions. This is also something that you would need to know if you're piecing together, you know, the solution of an initial value problem. So for instance, you can't have, let's consider a circular drum head again. At the edge of the drum head where it's affixed to the rim, the membrane's not going to move, it's fixed. So that's where you would have to piece together your zeros. So no closed form solution, those are solved numerically. Mathematica could do that for you. The n just means give me the numerical answer. And you just ask for the, in this case, the first zero of the 0th Bessel function. So that's this one right here, 2.403 looks right. So if I wanted to find this point, that is the first Bessel function, and that would be its third zero, first Bessel function, third zero. sorry, that's the third zero. The 0th zero is defined to be the one there. So that's 10.17. That's about where it's looking like it's going to hit. So that's how you would find those. And again, you know, if you have known initial boundary conditions, if you have boundary conditions, what you have to do is scale your Bessel functions so that they do what you want them to do. And unfortunately, that has to happen numerically. Right. So showing that all together for a couple of zeros of, in this case, the first Bessel function. So there's the 10.17. And these are not regularly spaced. So even though they might look like it, I'll change that to 0, and you can see they're really not regularly, whoops, spaced. Got to change both. Kind of junky code. Right? So, okay, but aside from that, the way that you think about using them is like sines and cosines, except the properties like the zeros and the max and min values aren't as obvious. So you generally just go to a table. Okay. So any questions about that? Okay, so now I just want to talk about how we would use this in 1, 2, 3 contexts in differing levels of complexity. So one is just knowing that, hey man, that's got to be the solution, just in case you're ever confronted with this problem. And then secondly, for somebody hitting a circular drumhead, we'll piece together an arbitrary solution out of the building blocks, the Legos of Bessel functions. And then finally, actually we'll do this first, just so I can show the video and see how well it works. We'll actually derive Bessel's equation from scratch for a physics problem that you are not allowed to solve in mechanics. So this is one place where you would see Bessel functions. So when you did waves in optics, you were allowed to solve the problem of a thin slit, and you probably saw that in lab. So there was light, laser light, so coherent laser light, one wavelength, shining onto a slit, and what you were led through is this argument that, well, if the slit is of finite width, light from the top of the slit or one side of the slit is going to interfere with light from the middle of the slit and the bottom of the slit. And it turns out just the single slit problem is surprisingly complex. You guys did that for a linear slit. So if I shine laser light on a circular aperture, instead of the traditional sine theta that you got, if you went through the equations, you would get Bessel functions. And this is just, you know, I didn't want to write it out. So this is just the series expansion that we derived for Bessel function of the nth order. Right? And this is what this looks like. So this is what a Bessel function looks like. So this is what you guys should probably have down at this point. Is there any J0 in this Bessel function? So the circular aperture. Yes, I see nodding, which is great. So I know that there's J0 in this circular diffraction pattern because it starts at non-zero, right? So I know that this would contain some J0. Great. So if you're there, you're in good shape. And then you would have to follow the math of circular diffraction, which is not terrible, but there are better things for us to do. So that's one place where you'd see this. Okay. Next thing, we'll see how well this shows up. This is somebody's, yeah, I think like a mechanics lab somewhere on Earth. And they actually demonstrated this, and it's a really cool video. So we'll actually go through the theory behind it to get to Bessel's equation. This is somebody who rigged up a wire. So this is not an ideal string. It's actually got mass. So an ideal string for us in waves and optics and vibrations was something where you could ignore the mass. So we're not going to be able to do that anymore. And then this thing is going to be spun. So basically hooked up to a power drill. And what you should see is the spinning string will actually take on Bessel functions. So they should look like Bessel functions, and then we'll derive that. So I'll just let this play for a couple of minutes. Can you guys hear that okay?
I don't hear any audio from the video.
Yeah, I don't hear it.
Okay. Let's see.
It might be Zoom sometimes only shares like video and not audio, so.
Sometimes you need to check something in order to share audio as well.
Yeah, it lets me. So I shared system audio and it didn't look like it worked. So I'll just narrate what he's saying. So this is a beaded wire, and then there's a power drill attached to a variable voltage generator, and he's connected it to a strobe light so that the strobe light and the drill are actually rotating at the same frequency. So instead of just like a spinning blur, he's got it rigged up so that the strobe goes off every single time the drill is at the same part of its rotation cycle. But already, can you guys see the zeros in the Bessel function? Okay, so now the strobe's on and it's rigged so that the strobe and the drill are in phase. So that's Bessel function with 3 nodes. And then scanned up the frequency to get to 4 nodes. So the 4 nodes you can pretty clearly see. And then probably at some point, you know, the physical reality of the beaded wire is going to take over. And so what he's doing is comparing the theoretical zeros to the ones that he measured. And turns out the agreement with where the zeros should be and the theory behind it looked like 5%, so that's pretty good. So I'll post this so you guys can listen to the whole thing. And the theory is in the first 3 minutes. Okay, so why would this be Bessel functions? So this is an example of how I would get this from a physical system. And like all physics problems, we got to put the fine print on. So we have a mass per length. So the string has a mass, the string has a length. We're going to define the linear mass density as the easiest way of doing this is not 0. So this isn't one of those ideal pendulum springs that we had in waves and optics where the string itself or light and extensible rod is massless. And that's going to be important because the reason it's a Bessel function is because it's got more tension at the top, right? At the top, the string is being pulled down under the weight of the bottom of the string, and it's got less tension at the bottom, which is why, you know, in some puristic sense, you kind of like, oh yeah, that's why the nodes are farther spaced at the top, less tension, and closer together at the bottom. Turns out to be Bessel function-y. So here's our picture. And this is how we're going to define the coordinates. So that's just the z-axis. And we're going to be spinning this with some angular frequency omega, just to keep 2 pi out of our life. And the string is going to do something like this. We now know it's going to be like a Bessel function. And our coordinate system is going to be described in a slightly funky way. So here is the point R of z. And when the string is at rest, the bottom of the string is going to be, the bottom of the string is going to be, so I should draw something a little bit different. Yeah. So the bottom of the string is going to be z equals 0. So z is going to start down and increase as we go up. So as opposed to calling that 0, I'm not going to do that. It's going to make things a little bit tougher. Okay, and then the last bit of fine print. So far, these are not even assumptions. Like, this is how a real string actually works. The assumption we're going to make is that all of the angles in the rotation of the string are going to be small angles. Which means at no point is the curvature of the string at any point bigger than would allow us to use the small angle approximation, which is maybe about 15 degrees. So, you know, look back at that video and maybe you're like, I don't know about that. But it turns out small angle approximation is not so bad. Okay, so this is just a mechanics problem, which means that F equals ma. So now what we have to do is choose a good coordinate system. So if we're talking about a steady state solution, we're going to have, you know, hard to draw on a 2D chalkboard, but we're going to have a radial direction, which is pulling towards the dotted line. And then we're going to have a vertical direction. So in a standing wave, if I think about a single point along this, the vertical acceleration of that point is 0. So F net at some point in the vertical direction is 0. So all we care about is the radial acceleration, right? Think about each individual little delta d mass as executing uniform circular motion. So that's the part we care about. So F vertical equals 0, which means that we actually argued the opposite way. A vertical equals 0, right? For any individual point. So what we care about is F radial. So what is the force that's pulling this thing towards the dotted line, like the name of the force?
I think it's a central force.
Yep. So anything that pulls you towards the center is called the centripetal force, in the same way that anything that pulls you down is called the vertical force, or anything that pulls you, you know, along the x-axis, along the ground, is called the horizontal force. But out of the pantheon of forces like gravity, friction, whatever, what is it? Oops. So I have a piece of string, like I'm zooming way in on this, and I'm this little bit of string right in the middle. What are the possible forces that I have on this? Again, it's got mass, so there's gravity. Gravity pulls down, that's vertical. I don't care about that. What's the other possible force?
Tension.
Yeah, so we got tension. So really what's going on is if I look at a little disembodied piece of rope, there's tension at the top and there's tension at the bottom. And again, because this is a hanging string, the tension at the bottom is going to be less than the tension at the top. So if you're a little piece of string at the top, you're going to feel more tension because the rest of the string is like pulling down on you. Where if you're this last piece at the bottom, you have less tension. So the tension is not the same through the whole string. That's different than what you guys did if you derive the wave equation. So we'll call this T, tension at the bottom of some arbitrary piece of string. And then we also have T plus, again, the vertical stuff's going to cancel. We don't care about that. The only thing that's going to be different is going to be, there's going to be a little extra piece of radial tension. So that's why the string is going to rotate in a circle. Okay. So F radial, we argued away gravity. Gravity only points in the vertical direction. The only net force on this little piece of string is just going to be a little bit of delta t that points in the radial direction. And the traditional way of defining radial coordinates is away from the center line is positive. So I know that this is going to be a magnitude, and I'll just put the direction in by hand. So it's always going to point in the negative radial direction towards the center. And then I'm going to say, well, this is going to be the difference. You know, if I had a way of measuring the tension here and here, and I ask what the difference in between this angle, call theta 1 and theta 2, is, the only part that's radial is going to be delta t sine of theta 1 minus theta 2, the small angle approximation. That's going to be annoying to write. So I'm just going to define theta to be the difference. Oops. Okay. So theta is the little bit of extra angle, the angle of bend of this piece of string. So that's what theta means. So sine theta. So now I'm going to use the small angle approximation a second time. And we have a little bit of ds. This is our theta. Now notice the whole triangle could turn and rotate as we go up and down the string. What this angle is the difference in between how the top of the string points and the bottom of the string points. And there's dz and there's dr, the radial direction. And because we have a small angle approximation, I can do the following. I can ignore all of that stuff I just said and say, because we're working in the small angle approximation, I can just say that that's the actual angle. And I can also say that sine theta is equal to tangent of theta, approximately equal to tangent of theta, and is approximately equal to theta itself, provided I'm measuring theta in radians. So I have minus delta t tan theta, or theta. I'm going to say tan theta is the best way of describing this, because tan theta is dr over dz, just by looking at this triangle. So the little bit of radial deflection of the string divided by the little piece of vertical deflection of the string. So in the small angle approximations, I should approximate that. Actual difference in newtons, and then dr dz. Okay, so that's the hand wavy junky part that, you know, you would need to think long and hard about whether or not that approximation is valid. And to be honest, looking at that video, it seems like we're going to stretch it a bit, which probably explains, you know, systematic issues in that guy's results. Okay, so what we have is f. This is f, and now we got to work on MA. So MA, we have a little piece of mass. So a little piece of mass is going to be dm. So that's the mass of this little segment of string whose acceleration we're looking at. And then acceleration is centripetal acceleration. And I can say that dmass is my mass density, lambda, times, again, a little piece of the length, dz. Right. Again, small angle approximation, dz and ds are about the same. And centripetal acceleration is r omega squared. That's v squared over r, but written in such a way that we can use the angular acceleration. So that is v squared over r. So we have F, we have MA. That was all we needed. Okay. So overall, we have Newton's second law that looks like this: minus delta T dr dz equals lambda dz r omega squared. I don't see anything that even remotely looks like Bessel's equation yet. But I'm going to point out that we actually have something in here that's useful for us. We actually have, again, in the small angle approximation, what is the tension on this rope? Well, the tension on the rope is, because it's not accelerating in the vertical direction, the tension is just whatever I need to do to balance gravity. So the tension is equal to, mg. And the tension, therefore, is we have m. So the mass that's pulling down on the bottom of the rope. So the mass that's pulling down on the bottom of the rope is lambda times z. So that was the choice of this z coordinate. So there's no rope pulling down on the bottom part. There's basically lambda zg pulling down on the top part. So we have, again, really just abusing the small angle approximation. So it's amazing this works as well as it does, in my opinion, at least. So we can rearrange this and we can get calling this like delta, big delta for a second, delta t over delta z dr dz, and then putting the minus on the other side, minus lambda r omega squared. So far, just a lot of approximating and, you know, the fake physics acrobatics of interchanging deltas and d's. So we're going to do that one more time. And what you end up with in a continuum limit, so I'm going to replace star here and essentially have d by dz of t, but I'm going to call t lambda zg. dr dz equals minus r omega squared. It's a really funky omega. Okay. So this is the point at which, if you watch the Sturm-Liouville stuff, I actually already know that this is a Sturm-Liouville type equation. I see d by dz, and then I have another derivative inside of it, and I see my eigenvalue, and I see r. So what this is going to do is this is going to give me a function of r, and the solutions are going to be a set of a basis function set. So orthonormal. Okay. So pulling that last one up, what we're going to do is just put it into the standard form of Bessel's equation. So we had d by dz, what we replaced tension with to get the z. So the point of that, again, was to note that the tension is going to be proportional to how far down the wire you are, right? So this is tension, and then dr dz equals minus lambda omega squared, grouping that all together. And again, what we're looking for is r as a function of z, how far away from the center axis you are as you go down the wire. And it doesn't take too many more steps because I can just take this derivative through, product rule it, lambda and g are fixed parameters and then realize something kind of neat happens. All my lambdas go away. So the mass density vanishes. So you can actually see that right here. So lambda would divide out on both sides. So what this is saying is that if you were to do this with a different string, like all strings of all different mass densities, you would actually get the Bessel functions with the same zeros. They would all look the same. So pumping this through and rearranging a little bit, I get two derivatives dr dz squared plus dr dz. And then let's group things this way. R squared over g, r equals 0. So this is Bessel's equation. And I will rewrite Bessel's equation so we can see that. So our standard form looks like this. So I have to do two things to map this actually completely onto Bessel's equation. What are they?
You can multiply the entire equation by z. That gets you a z squared on the second derivative, a z on the first derivative, but you only have one z on r.
Yep, so that's a good start. And we have this funny second term that isn't really cooperating, right? So we have an issue here. So this is something that will show up in one of the homework problems too, is that this isn't really like obvious that it's Bessel's function or Bessel's equation. So it turns out that if you do this and work it through the derivative, so if you define x to be, the 2 omega is just kind of bookkeeping, but root z over g, and you put that in here, you will actually get Bessel's equation. So there are a lot of things that actually don't look on its face like Bessel equations that are. And I'll, if we have time, I'll write down this really neat theorem that basically says you can write any second order differential equation up in terms of Bessel's equation if you're willing to make these sorts of substitutions. You're willing to define x in terms of z to some power. And it turns out that will do things here. Right? So completely not obvious at this point. And you're thinking like, if I just multiply by z, I kind of get the first two terms, but the second term doesn't work out. But this change of variables actually turns out to put us into Bessel's form. And as a consequence, we get to just say that J nu of X are solutions. Okay. So it's as easy as that. Is like you see Bessel's equation, you just write down appropriate solutions. So I think this is the best time to write down this sort of magical theorem about arbitrary second order differential equations. And then we'll go on to something where it's not as obscure. Where's my... call it a theorem. I don't know if it gets elevated to theorem. So this isn't every second order differential equation, but it certainly takes care of a lot. So I didn't, you don't remember offhand, but I think the reason I didn't show you the first couple of minutes of that video is he would have ruined the surprise. So again, not obvious that this is Bessel's equation, but this, anything that you can put into this form is solvable as a Bessel function, provided you're willing to scale it and provided you're willing to have these goofy powers. So that's a C. Okay, so you can scale the variable that's inside of the function itself. And that's what it turns out you can do here. So let me give an example of that, because this is, in some sense, as powerful as beta and gamma integrals. But any questions about mostly I wanted to show you guys the derivation and then use this to introduce this really neat trick where just about any second order differential equation has Bessel function solutions. Okay, this shouldn't actually be surprising. Any function that you guys can dream up has a Fourier series expansion, right? Up to, if it's got some like insane pathology with an infinite number of discontinuities or something. It turns out that any function that you can dream up has an expression in terms of any orthonormal set of basis functions. So the fact that you can describe the solution to any second order differential equation in some sense as sines and cosines, or in some sense as Bessel functions, shouldn't be too shocking at this point in the quarter. Unless it is, then let me know. Okay. So let me give an example of, in general, without a bunch of physics constants, which I think will kind of muddy waters, of how this theorem would work. And then we'll talk about what those ends are and modes on a drumhead. And I think that would be good for today. Okay, so I do the following. I compare the coefficients in the theorem to the coefficients in my second order differential equation. And it's literally just looking. So what's in front of the y double prime term? Nothing. So we got that for free. What you'd have to do otherwise is divide whatever is here to put it in this form. So that's good. So looks like we have on the constant term, okay, we've got no y prime term. The only way we could have no y prime term here, no y prime term above, is that 1 minus 2a has got to be equal to 0. So that vanished. And then we have no 1 over x squared term. So that means that that numerator also needs to vanish. A squared minus product PC quantity squared is also equal to 0. And then looking at the last term, so clearly C equals, or because it's squared, 2C minus 2 is equal to 1, and BC squared equals 9. So remember, we got a squared here. So BC quantity squared, I've got to match that onto that coefficient, that equals 9. And then because we're squaring again, 2 times C minus 1, looking at the power of the x, that's equal to 1. And that's enough. So that is, kind of working through, you can see what A is immediately. A has got to be equal to 1/2. Now that we know, and C is equal to 3/2 by looking down there. And then once we know A and C, we can figure out B and P. So B equals 2, and P equals 1/3, 1/3. And therefore, y of x equals x to the 1/2 power. And this is the part that we've talked about in enough detail. So you can multiply this whole thing by a constant. The constant would come out. So we get an unknown constant. Just call it A because I'm uncreative. J sub P, what's P? P is 1/3. And then 2x, so B is 2, and then x's power is to the 3/2. And then we would also get these other things, which we're about to talk about now. Keep my notes in better order. Okay. So surprise after surprise after surprise. We didn't say that these needed to be integers. They don't need to be integers. What needs to happen is we need to modify our series solution, but we already know how to do that. So I'll just write how that would work for non-integer p, and then talk about what the Bessel functions of the second kind are, because it only really makes sense what these ends are after we talk about what happens when j equals 1/3. Okay, so theorem, I don't think that's an easy one to prove, so we'll just state without proving. Okay, so last 2 topics, and then we'll spend 20 minutes on circular drum heads, which will be nice. Okay, so the two remaining questions. So remember those k's came from a separation constant, right? And there's no reason that they needed to be integers. So the reason that they were integers in Legendre's function essentially is because if I have a cosine of theta, which is what we were using when we derived Legendre's equation, we were talking about the axial behavior of the Laplacian in spherical polar coordinates, is that I have boundary conditions. Like I can't have a cosine wrap around and not equal its value after I wrap around. And the reason that, for instance, the Fourier series have integer values that n goes from 0 to infinity is because sines and cosines, if I have a repetitive function, I have to end up back where I started. So for periodic functions, generally you end up with integer values of these separation constants. We're not wrapping around with Bessel functions. Bessel functions can go from 0 to infinity. So that's kind of the shorthand that, you know what, k didn't necessarily need to be an integer because it doesn't have to be periodic. You know, if I drop a stone in a pond and the ripples go out, you know, the ripples could be as big as the pond, which could be very big. So what that lets us do, and we already did the work, I'm just going to show the recursion. And you guys are about to derive, without a lick of work, the equation. So we did this, more or less, for Bessel functions of the first kind. So we got the indicial equation. And I said, look, if you know something about series, you can actually solve this as a closed form. And it would look like this. So this is one way of actually just deriving, straight up deriving or defining the Bessel functions. Okay, what's the problem if p isn't equal to integer value? I have no problems here. What do I actually have a problem with?
The factorials get weird if you don't have integer arguments.
Yeah, but you know what? What do I do? I just like literally replace one thing. If I don't have an integer in a factorial, what do I put instead, actually?
You use the gamma function.
Yeah, so we actually, if it seemed like the gamma function was a little bit far afield, it's not, because this thing shows up and saves your life a whole bunch of times when you're working with these types of functions. So I'm not going to do that anymore. I'm not even going to start writing it. So all I do is I replace my factorial exclamation points with gamma functions. So these are gammas. And we just got to remember that silly like +1 thing. So this is gamma of s plus 1 is s factorial. So this is s plus 1 factorial. And then s plus p plus 1 gamma function. And fractional powers, non-integer powers of x, like that's not an issue. It's really just the factorials. So this is the fundamental definition of Bessel functions of non-integer powers. You know, it turns out that you could have defined them this way in the first place and just said like, look, I made up these things called Bessel functions. Turns out they're useful. And likewise, if you wanted to talk about a negative value, negative values are okay. Okay, we didn't talk too much about this, but does anybody remember when you guys plotted and worked with Bessel functions, or maybe remember that reflection formula? Does this solve all of our problems? What's gamma of -4? Is that defined or not? Yeah, so we still have problems. So we've gotten from integers to fractional values, and we actually have negative values and negative fractional values, but negative integer values actually are poorly behaved too. So this is what those gamma functions of the second type are. And I'll just write this. I just want you guys to know they exist. So this is what the n's are. So a lot of naughty stuff happens. So for instance, j of minus p of 0 is infinite if you look at the series expansion. So that's an issue. And then gamma of negative integers is undefined. That's an issue. And so what people have found is that there are Bessel functions of the second kind, also called Neumann functions. And I don't think it's going to be helpful for us to go through the argument in total. So we're going to define these things, and it turns out they fix a lot of these problems. So these are alternately, even I think they have a third name, like Weber functions or something. The n is for Neumann, or Bessel functions of the second kind.
I've seen them written with a big Y, which is odd. Like I have no idea where that would come from.
Yeah, the Weber functions is a Y. Yeah, the n and the y are different. So I think it's because if it's the Neumann I'm thinking of, he's like a 20th century figure. And probably what happened is he was really famous and he was really good at kind of marketing his achievements. Like you'll see him credited as the inventor of the computer, like everything digital computer, ENIAC. He never touched a wire in his life. Like he just hung out with those guys and wrote like a 100-page paper on it. And to this day, there are people who are pissed off about John von Neumann being the father of computing. So it might have been the Y was archaic terminology and somehow Neumann like rebranded it in his image, if it's that Neumann. But yeah, you'll see Ys too. And I think Arfgen points that out. They're pretty good about going through the historical nomenclature. So Bessel functions, no greengrocer's comma, of the second type. And I'll just point out one feature. So this is how the blowups in the regular Bessel functions of the first kind are dealt with in the Bessel functions of the second type and how they're defined. So we could say that np of x is equal to, and if you remember the recursion formula for the gamma function, you can see like, oh, I kind of see what's going on with this. So jp of x minus j minus p of x over sine pi of p. Okay, so what we have essentially is we get a blow up at negative integers, and it's regulating these blow ups at negative integers. So you could do like a L'Hopital's rule type analysis and say like, oh, this thing actually has. So the Neumann functions actually also have shitty properties, but they have shitty properties in a different place. I just want you guys to know they exist. Okay. Any questions about that? Then we'll finish with one, come back to sanity and talk about physics. So this is, again, how you would see this in the context of vibrating modes of a drum head, circular drum head. Okay, so let's look at the answer first. So these are the normal modes of a circular membrane. Like if you hit the thing off center, you might see something like this. You don't hit the center of the drum. If you hit the center of the drum, you might see something like this. And they're animated in time, so you can see low frequency, higher frequency, right? If you hit a drum and it produced a pure tone, have you guys ever listened to a sine wave generator hooked up to a speaker? It's not musical. It's a terrible sound. And drums aren't the most musical instruments, but clearly they don't sound like that. So if I hit a drum, I'm going to be a little bit off center. I'm going to excite multiple modes, even if I am on center. The real answer is going to be that there's some mixture of all of these in the sound of a drum being struck, including these cool higher modes. So I want you guys just stare at this hypnotic vibrating stuff for like a minute, and then I'll show you how this whole thing comes about with Bessel functions. And you should just know that this is essentially a 2D analog of Fourier series stuff, where there's some function and we're just going to represent it in terms of a collection of fundamental units. Okay. So we've got circular modes of the drum head, vibrating, and what's true is that these satisfy the wave equation. And we need to come up with some, this is going to be a really wretched picture. I don't know how to draw that stuff, but hopefully you're kind of with me. Okay, imagine that there's some like wiggling going on. Okay, so here's a drum head and it's struck. What coordinate system should I use? And what's my dimension going to be?
You could use it would be two-dimensional with polar coordinates.
Yeah. So we'll call this rho and phi. And what this is u of rho and phi is the height or displacement of the membrane. So if u is a large negative number, that means the drum head is really depressed at that point, rho phi. And if u is a small positive number, it means it's a little bit above the center line at that point. So that's what we're trying to find. Okay, so so these would be snapshots, right? But as you saw, those circular membranes that we were watching were animated. So if these are a function of time too, if these evolve in time, what we really have is u of rho and phi and t. Yikes. So we're in two spatial dimensions, and then we get one time dimension. So we have boundary conditions. As well, which say that we're stuck to the rim. So we'll say that this circular membrane has a radius r. So my boundary conditions would be u of r, phi, and t for all t, doesn't matter what time we're at, is equal to 0. So this is an initial value problem. We've got boundary conditions. We would have an initial value as well. So we would also have at t equals 0, u of rho and phi is equal to some function, right? Like the moment the drumstick hits the thing, you take a snapshot, and the question is, how does that evolve in time? So you move this thing and then it makes noise. Okay, so this is a full boundary condition initial value problem, right? And it turns out because we have a second order differential equation, that's actually not going to be enough. We also need to know the derivative, the time derivative at every single location on the drum head. So those are the boundary conditions, and these are what are called the initial conditions. Okay, so now it's as simple as the following, is that we have the wave equation. That's two time derivatives. Ooh. Okay, I'll write it out. D squared u dt squared is equal to v squared. So that's the speed of sound or speed of propagation of waves on the drumhead, Laplacian u squared. How am I going to solve this? Don't worry, we're not going to do it. But how theoretically am I going to solve this?
The separation of variables.
Yeah, so I have u of t and rho, well, keep the same order of rho and phi and t. It's going to be equal to r of rho, capital phi of phi, and big ol' T of t. Okay, so I have a t thing. I'm going to get another separation constant. Okay, fine, we have another separation constant. What are the solutions of this going to be? What are the solutions of the r of rho going to be?
Those are going to be Bessel functions.
Yes. You just solved a second order differential equation in 3D. Good job. What are the phi of phi going to be? So this one, they're easier, but they're not as easy. And the t of t.
Well, the time functions are just going to be complex exponentials.
Yep. Or if I'm not feeling adventurous, I could do sines and cosines. Right? They just wobble back and forth. Sines and cosines are complex exponentials is the more elegant way of writing them. And then, remember staring at that picture of the modes on the drumhead? Is there anything you can think about the phi behavior? Or if you remember when we actually did this in separated variables. So it turns out separating phi gave you an equation that looked a lot like the one that you would get from here. It would look like phi double prime is equal to like minus separation constant alpha squared phi. What are the solutions to that?
Those are also complex exponentials.
Yeah, EI alpha t's, right? Okay, so in this case, the alphas are going to be integers or spaced by integers, like 2 pi integer values, because what needs to be true is if I wrap once all the way around the drumhead, I better come back to where I started. So this is going to be a discrete sum. This is going to be a discrete sum. The Bessel functions are also going to be a discrete sum. So this is how you do these type of problems. You just understand that, separation of variables occurred, and then you know what the solutions should be. So I'll write down the entire solution of this, okay? And then you should be able to see like where all of these parts came from. Let's see. Yeah, sure. So therefore, and this is it, we weren't like cheating anything. This is really the solution of, the general solution of the differential equation. We're going to have a sum over three so-called, or some so-called quantum numbers. And remember, every time I split two variables, I get one new coefficient or one new constant. So I'm going to ultimately only need two separation constants, right? One when we split off the time from the other two, and one when we split off the phi from the row. And the way that you parse that is however you want. You could put one on the R, the other one on the N is the easiest way of doing it, and then saying T depends on both. So this is what the solution looks like. And we know that the RMs are Bessel functions. And conceivably, we could have these, but I'll write it because we didn't go too far into the properties of the Neumann functions. These don't exist in this problem. Okay. And then we have phi of n is equal to, I like the complex exponential idea. Two pi n phi. And then T of T and M is going to be equal to E I omega nm T. Okay, and I don't have to put a coefficient on this because these two will combine to make the coefficient CNM. So that's it, and I just multiply them together. So each individual problem really honestly isn't that difficult. So what is omega nm? That's 2 pi times the frequency nm. So, last thing we'll do is just look at this, think about it, and see if you can see all of these parts in the solution. So this is how separation of variables works. Okay, actually one more thing to mention is that what I have to do is I have to make sure that I satisfy my boundary conditions. So this is how alphas are chosen. So alpha makes u of r theta t equals 0. So the alphas make you fixed to the rim of the drum. And well, we already did the 2 pi n's. And the collection of these coefficients, C and M, make sure that our initial boundary conditions are met. So u of rho phi at 0 and u dot at rho phi 0 are the two functions that we chose or were given to us. Phi. Okay. So the alphas scale the Bessel functions so that they die off at the edge of the drum, and the collection of coefficients do what they need to do to satisfy the initial value problem. Okay, do this for 30 seconds each. Stare at this math. And now stare at this animation. Do you guys like see all those parts in there? So the higher and lower frequency. This is a constant function that capital phi of phi, this is constant, it never changes. But here in the second mode, you can see that phi is equal to a sine. At any point in time, we go up and down, so there's a full mode. And then here we can see that phi has multiple modes as we travel around the circle. And then, it's hard because it's a moving target, but especially here, you can kind of see Bessel functions. Bessel functions with 1, 0, 2 zeros, 3 zeros. And that's exactly what's indicated here, 1, 0, 2 zeros, 3 zeros. And those alphas are chosen to make sure that the thing is 0 at the rim. Okay, so I'll post a teeny tiny video on the remainder of the Bessel function zoo, so modified and maybe spherical Bessel functions. But to be honest, I don't think you don't need to go through that to do the homework. And then on Thursday, we'll have complex analysis and conformal mappings. So any questions that come up on the homework, I think most of that stuff's straightforward, like applying the Cauchy-Riemann conditions, for instance. but from that, this isn't going to be amazingly helpful.